I'm Andrei. I'm a senior software engineer at Adobe. I'm part of the Adobe Experience Platform Data Lake team and working in big data and distributed processing. I'm trying to contribute to open source projects like Iceberg, Delta Lake, Hyperspace, and recently I've been enjoying doing stuff with Polaris and Data Fusion. Today, I'll be discussing the purpose and benefits of Apache Arrow. Apache Arrow and how it can provide a performant option to process datasets. The agenda is the following. We'll get a bit into Apache Arrow format and its available implementation. We'll discuss the differences between them. We'll switch to query engines and make use of Arrow format. We'll look at two of those, both written in Rust. We'll look at Data Fusion and Polaris. We will dive into some queries and see how similar or different they are between the two, and we'll compare with Apache Spark. Lastly, we'll discuss the gaps and where to use which. So let's jump into it. First, what exactly is Arrow? Apache Arrow is an in-memory columnar data format that was developed to provide a common data representation for big data analytics systems. The format provides a standardized way of storing and exchanging large data sets, which is especially important in the world of big data, where data is often generating from many different resources and systems. One key benefit of Apache Arrow is that it's built for in-memory usage. Think about the efficiency of C++ array type, but on steroids with all kinds of inner types and nested structures. Arrow has these types well defined and built for memory efficiency. Now, being built like this, zero copy aspect can be achieved and serialization and deserialization minimized. Another very important benefit of Apache Arrow format is its use of columnar storage. That is an efficient way of storing data in columns rather than in rows. This has several advantages for big data analytics, including faster data access and improved compression. By storing data in columns, Apache Arrow allows for more efficient data retrieval and analysis, which is critical for big data application. Another two related and important aspects of Apache Arrow are cross-platform compatibility and language agnostic aspect of it. Apache Arrow provides a common data representation that can be used across different programming languages such as Java, Python, Rust, C++, etc. This means that data can be easily exchanged between systems regardless of the programming language they use. Apache Arrow is a structured format, and this means that there are well-defined types that should be used to leverage performance when operating on types. So operations on integers are differently optimized than on strings or byte arrays. This structured aspect helps minimizing the overhead of serialization, deserialization, type transformation, and memory footprint. It is also an open source project, which allows for a large and active community of developers to contribute to its development and advancement. Apache Arrow format has a strong ecosystem. It is integrated with many popular big data analytics tools and technologies, including Apache Spark, Apache Flink, Hive, etc. This allows developers to easily integrate Arrow into their big data analytics pipeline and take benefits of all these advantages. Now let's get a little bit more into this concept called columnar format and try to understand its benefits. So on the top row, we have an example of a data set stored in an already well-known row-based storage. Groups of entire rows are stored in pages inside files. In this simple example, the first two rows get into file 1, next two in file 2, and so on. On the bottom, we have the columnar format stored in files. As you can see, the whole column 1 gets into file 1, part of column 2 in file 2, and so on. We can see the difference in how the data is laid out on the storage. But now let's look at a couple of queries to understand how these queries work with each these kind of formats. First query is the well-known select star from table where predicate. So what this will do is will load a file, in this case file 1, that has 2 rows. We'll keep the row that match the predicate and drop the second one. In this case, one single file open. The same query in the second case of columnar format shows that it will load 3 files. file 1, file 2, and file 4, and drop the majority of the data, keeping one field from each file, in this case, 3 files open. Note that it's not that efficient in this case. Looking at the second query, we do an aggregation that things look different. For row-based format, it will have to load a lot of files, file 1 to file 4, and then drop the majority of data. In this case, lots of files open, and to be more accurate, all files are opened. Same query on the columnar format shows that you load only the files containing the column on which we do the aggregation. No data dropping, only needed values are loaded. We can see that from the use case where the 4 rows are needed, the best storage is the one row based, while for use cases where aggregations are predominant, the columnar format is desired. Now there are other benefits of a columnar format, and these are because of the fields with the same type are close one to another, mostly in the same file, data become easy accessible, no need to switch between different types. And O1 random access time is another important benefit that comes with this format because it's in memory and columnar, data is stored sequentially, and it has well-defined types with size. So when doing an access, it will know where to go to fetch the data. Now, the single instruction multiple data vectorization is possible with columnar format. Set of fields values will be processed in parallel in modern processor. And then we have the zero copy access, which means less serialization, less memory consumptions. Now, there are quite a few formats that are columnar, like Parquet, ORC. There is the Arrow feather format. So yeah, it's pretty used. In terms of implementation, let's have a look at 2 languages, C and C++, C++ and Rust, and see how we stand with Arrow. There are DuckDB and Velox databases that have their own implementation of Apache Arrow format in C++. There is also the official libarrow library in C++ that includes Arrow streaming execution engine. On the other side, on Rust, we do have the Apache Arrow data fusion query engine that makes use of Arrow RS, and Polaris data frame library that uses Arrow 2. From this point, we will be focusing on Rust and Arrow, leaving behind C, C++, and other general aspects. So let's first go on the official implementation of Apache Arrow in Rust called Arrow RS. So currently, this implementation is at version 34, and by that number, looking at that big number, we can see that heavy development is happening on this repository. Some of the main modules and libraries that are available with Apache Arrow RS are Arrowflight, a high-performance data transfer framework that utilizes Apache Arrow memory format, and Arrow Object Store, focused, easy to use, and high performance, asynchronous object store library interacting with stores like S3, Blob Store, Google Cloud, etc. Now, Apache Arrow RS supports all major file formats like CSV, Parquet, JSON, Arrow, ORC. Switching to the other implementation called Arrow 2. Arrow 2 is a transmute-free Rust implementation of Apache Arrow format. It's written by Jorge Leitao. The project does focus on simplifying the use of Apache Arrow by removing the need for data conversion steps. So that's why it's called transmute-free. It also optimized for parallelization with single instruction multiple data vectorization, featuring more types than Arrow RS. And it's also memory safe due to Rust. Arrow 2 has libraries for accessing CSV, JSON, Parquet formats. It supports the Arrowflight RPC protocol. Development is going fast in this implementation, and it is used in Polaris. And possibly in the future, it will be used in data fusion because I've seen some works going in that direction. Now, you may wonder, why Rust? Why was Rust chosen in these projects? So Rust gives memory safety. From its conception, core pillar in Rust is memory safety. In fact, that's why Rust has been built to have the C and C++ speed with memory safety. The concepts of borrowing and ownership are core elements in Rust. Concurrency, Due to the same borrowing and ownership concepts, and together with mutable and immutable concepts, concurrency issues are eliminated or minimized. Performance is very, very similar and close to C++ code, so no garbage collection downside here. It is cross-platform. Rust code can be compiled on so many platforms, starting from embedded microcontrollers, even bigger processors, and going up to silicon processors that are new right now. So Rust is a very powerful language and started gaining notoriety and traction in big data distributed processing due to these advantages. Now let's switch a little bit towards these engines. First, we'll look at Arrow Data Fusion. Data Fusion is an open source query engine designed to be fast, efficient, modular, and is based on Arrow format. It's a modular and also extensible architecture, makes it easy to add new functionality and features. This enables users to customize this engine according to their specific needs, and sometimes use parts of it in their products or flows. For example, InfluxDB's latest engine is based on Data Fusion. Because Data Fusion is built using Apache Arrow columnar memory format, it does provide a high performance output. The columnar format allows efficient memory utilization and enables Data Fusion to process data much faster than traditional row-based processing engines. Data Fusion provides built-in connectors for various data sources, including CSV files, Parquet, and Apache Kafka. This comes also from Arrow format. This enables users to easily query data from different sources without having to write custom connectors. Lastly, but not least, besides the data frame API, it provides a complete SQL engine that supports a wide range of SQL queries, including joins, subqueries, filters, and aggregations. It also provides support for standard SQL syntax and ANSI SQL functions, making it easy for users to work with the engine. Now let's look at some code and how to use Data Fusion with Data Frame API and SQL. So first we need to create a session context, which is very similar to what Spark does. All future actions will be tied to the context. Then we read a Parquet file with read Parquet and select only the needed columns by specifying the collections of columns. In the end, we do a filter and show the results. Down is the same query, but expressed with SQL. The same first step of creating a session context is present. Next, we need to register the Parquet file as a table inside the session context with a specific name, in this case, my Parquet table. And that name we can later use in our SQL queries. Then we define that query similar to any compatible SQL database. And we show the results. As you can see, this is pretty close to what we do in Spark and other engines. And it's pretty neat to be able to have both the Data Frame API and SQL available in Data Fusion. These are just simple examples of how Data Fusion can be used, but it does support complex queries like aggregation and joins, and I'll show you that a little bit later. But for now, let's look at Polaris, the new kid on the block. Polaris is a library that provides data manipulation and analysis for tabular data sets. Polaris is built on top of Arrow 2 library. It is fast, and we will see a bit later in some slides that arguably, it holds the crown on performance. It is very easy to use, and it has Python bindings and can be used similar to pandas. Performance-wise, for the majority of queries, Polaris has a higher efficiency than Data Fusion, but yet it depends from query to query, and I'll show you that a little bit later. Besides the Data Frame API, similar to Data Fusion, it provides a SQL engine that supports a set of SQL queries, including joins, filters, aggregations. Currently, it's a bit less developed than Data Fusion, but Polaris community is working on it. Polaris can use multiple types of data sources, including CSV, Parquet, as Data Fusion and other engines, enables users to have these available and query data from different sources without the need of writing code. Now let's see some queries. In fact, let's see the same queries that we did on Data Fusion in Polaris. So first, let's load the data lazily. We do that with lazy frame scan Parquet method. This only defines the dataset and does not go to the disk. Next, we select our columns. And while we are providing the list of those columns, we can define the filter right there. As you can see, col1 filter col1 greater than 1. After that, we collect the result. The second example is the same use case expressed as SQL. The same lazy loading of Parquet file needs to happen. Then we create a SQL context, similar to Data Fusion and Spark, and register the data frame in that context as a table, giving it a specific name. Next, we define and execute our query and collect the resulting rows. So now let's switch and let me run some code, some Rust code, and I'll show you some aggregation and joins on both Data Fusion and Polaris. I'll have an example at the end that will be a little surprise. So here is a Rust project with some examples. We leave out the simple ones aside. We'll start with this query 2. So query 2 does an aggregation. Query 2 is this one here. So we try to get a mean, an average, and max value of a column of a table. Let me run this. So the tables that I'm using are provided and downloaded from Open Data Blend platform. They are free of charge. They are free to download and to use. They have anonymized data inside them. So it run over a data set that has about 1 gigabyte of data, about 80 million rows, and the result did take about 8 seconds. Now let's switch to the SQL one. And is this one, simple one. Select mean of this column and average and max of that. Let it run. So it should take the same amount of time and should bring the same results. And yeah. So it takes about 8 seconds or so. Yeah, I was saying about these data sets. I have 2 data sets. One is big, the other is smaller. Yeah. Now let's move to a more complex query. Let me switch to this one. It's query 3. I will run only the SQL version, but I can show you also the data frame version. So what we do is we do a join of 2 subqueries. So we want to optimize or pre-optimize, and we want only to take 10,000 values of the big data table. And we do want to filter by a predicate before doing any join, because join is very, very complex and very heavy lifting. We do that here, and then we do the same thing, the same approach on the right table, and then we do an inner join on those 2 tables. Let me run this. So this should take a small amount of time because we do that pre-optimization. So yeah, it did take about 150 milliseconds, which is pretty fast. The data frame version, it's here, it's pretty similar. We read a Parquet file, we limit here, and we do the predicate on driver vehicle key. The same on the second data set, and then we just join data frame 1 with data frame 2. That's all that we do. Now let's switch to the Polaris and show you. The first query is the same query with the aggregation mean, average, and max. We'll run this example. So yeah, the same table is used, the same data set are used in both cases. In this case, as you can see here, it takes about 2.5 seconds instead of, let me find it, 8 seconds, 8.3 seconds in Data Fusion case. Now let's switch to the last query, that is query 3. I want you to show something here, and I'll let it run. In the meantime, I'll explain you why. It will take a time. So query 3, I try to do the same query that I did in Data Fusion, but Polaris doesn't support subqueries. So I haven't been able to do that pre-optimization of taking only 10,000 rows. So what happens is it will take the whole 1 gigabyte table and join it with the other table, and that takes longer. At the end, we limit 10,000, but that's after the join. So yeah, that pre-optimization is not available in Polaris yet. So I've been running this a few times. It takes about 40 seconds, 39 seconds or 40 seconds. And it's because of that missing pre-optimization that I wanted to use. Yeah, 42 seconds. The last example that I want you to show is reading data from a Delta Lake table with data fusion. So we do have here this data dimension vehicle. I know it may be small, I don't know how to increase the font, but it has a delta log and the Parquet files here. So to use that with data fusion, we just say open table. That provides a table, and that table we will register here in the context and give it a name. Then after that, we can use SQL to query that delta table, delta lake table. Let me switch there and run it. Yeah. Now the integration between data fusion and delta lake table has some bugs. It's new and has some bugs. Some queries fail, some queries break. But yeah, it's nice that we can improve and have this running. I'll switch back to the presentation right now and go to the last slides that I have. We'll discuss about performance. Polaris beats everything in terms of performance. Second to Polaris is data fusion, and then I would say Spark. Now the file sizes that has been used, or the payloads, were from 500 megabytes to 50 gigabytes of data. These chart and these performance tests were provided by H2AI DB benchmarks. So now beyond 50 gigabytes of data, I would say we should go straight to Spark at this moment, because Spark has horizontal scaling and it's really distributed on multiple nodes. But both Polaris and data fusion are promising. Here is a comparison in terms of features. Spark is distributed, has vertical scaling, horizontal scaling. Now Polaris and data fusion don't have horizontal scaling because they are not distributed. Data fusion does have a project called Ballista that tries to make it distributed, but it's very hard to make it run and very complex to maintain. Yeah, I'll go next because the next slide is more interesting. Gaps and when to use which of these engines. So gaps, both data fusion and Polaris miss integration with different cloud storages and table formats. Now, there are some work that has been done in those areas. Data fusion is more advanced in that area. So I've been able to read with data fusion straight from Azure Blob, and also, as you can see, reading from a delta table. Other limitation is single node execution. Neither of those are distributed, and they are not enterprise ready yet. So features that we see in Spark are not available in Polaris nor data fusion. Now, when to use which one? If you have a large amount of data, above 50 gigabyte, go to Spark. You can distribute the workload on multiple nodes. If you have under 50 gigabyte, you can choose either Arrow Data Fusion or Polaris. Now, if you want a wide range of SQL features, go with Data Fusion because that's nicely implemented there. Under 50 gigabyte and Python, you go with Polaris. But again, some queries are still having issues. But yeah, that's how I would choose which one of those. In the end, here are some links. The example that I presented will be available on GitHub publicly, so you can be able to take them and use them. And the Open Data Blend datasets are available also publicly.